Okay. Ball's in your court. Yes, ma'am.
I think it was the number 34 on 5.1. Says to graph the Colombian study state solutions on the same piece. So does that mean to like split the equation up into two separate ones?
Yes.
And then,
So our transient solution is whatever is going to go away as time goes on. And our steady state is whatever persists.
then
Just graph them together. And then in the second one, sorry, the third part of that, it says to graph the equation of motion, which graphs just the whole solution. I think it would be useful to graph the whole solution and compare it to the steady state. So you can see, hey, here's where it's going to end up, but here's where we start, and this is the difference. But this is kind of like thinking about the solution as having multiple pieces. The transient piece in the steady state is the vanishing terms, the terms that are effectively irrelevant in the long run, and the terms that really persist and matter.
When we're solving for feet,
Yes.
and its sign, is phi tangent of C1 over C2, or is it the inverse tangent of C1 over C2?
It's tangent of phi equals C1 over C2. So it's the inverse tangent, right? Because that gives me back the angle I'm after.
But then if we were solving for sine,
It's cotangent, C1 over C2, or it's tangent C2 over C1. Do I have that in the right order? Is it C1 over C2 or is it C2 over C1? This is where I have to go back and look every time because I don't have this particular version memorized. Okay. And I just remember it because cosine goes with cotangent. It's the only way I can remember that setup. But even then, I write this formula down because I will got both.
I've been like kind of having issues with like assuming the particular solution, like what the particular solution would look like. Can you give like an example of like?
Let's flip open that variation of not variation, undetermined coefficients section. So that was section 4.4, right? So let's pull a couple of these. I've got non-homogeneous terms that look like. Pick one, man.
Can you do
E to the 2x cosine x minus 3 sine x. Okay. But the differential equation on the other side of that is y double prime minus 2y prime plus 2y equals e to the 2x cosine x minus 3 sine x. So the first thing I need is to find the homogeneous version. I'm going to get complex numbers. R squared minus 2r plus 1 equals -1. I just subtract 1 from both sides. This is r minus 1 squared equals -1. So I get 1 plus or minus I. I told you I like doing completing the square more, but do square formula if you want. That's fine. So that means that the corresponding homogeneous solution is C1 what? And C2. Now this is where I'm pissed off. Because the right-hand side for YP has, oh, wait, no, it's e to the 2x. That's perfect. That's different than this. I'm safe. There's no repeated things that I have to worry about. So I can say to myself, YP should look like e to the 2x cosine x some number and e to the 2x sine x. Because everything up here is now found down here. Does that make sense?
Yeah, can you do another one?
Yeah, Cody, for this.
What if it was just cosine?
That, if it's just cosine,
Yeah.
that would be fine. I'd still need the sine x down here. Why do I still need the sine x? Because what happens when you take the derivative of cosine? And when I get a derivative of sine, and since I'm going to use the first and second derivative up there, I'm going to need to have both of them because they keep flopping back and forth. And that'll actually help me get both of those coefficients when I set up this thing equals and then equate the coefficients.
And even if it's sine, it's the same.
Right. If there's only one, I need them both. Mia, pick another one then if you want to see another one. So 20, this sucker. Okay. Y double prime minus 2y prime minus 24y. Oh, double prime, y double prime plus 2y prime minus 24y equals 16 minus x plus 2e to the 4x. (16 minus x plus 2e to the 4x). Well, isn't that just disgusting? Again, let's start with the homogeneous version. And that's just a quadratic. But fortunately for me this time, this quadratic factors are negative 24 is 6, and 4 I want a plus 2, so it'll be a plus 6 and a minus 4. So I'm going to get the corresponding homogeneous solution is e to the 4x, crap, and e to the minus 6x. Well, now I'm annoyed because there's an e to the 4x on the right side. So I would say, well, I need something independent. Let's do an x e to the 4x. But there's also an x e to the 4x on this side. I'm going to do it again, which means I should guess x squared e to the 4x. So for this part in YP, I'm going to need at least that with an e to the 4x, right? But if I need a quadratic, I probably need the other two pieces as well. I don't need a plus C here, though. Because anything with just the plus C will get sucked into this. You can put it if you want, and I would just to be a completionist, but I'm anal retentive. That just takes care of the e to the 4x part. What about the 16? Yep. Now, I could be wrong. It may be that because this is just e to the 4x in here, to be independent, I should only have x e to the 4x. But if that's the case, then this a will work out to be 0. And that's all right. So I've gone a step further on purpose to try and get this to be different than this. But I think now that I'm saying that out loud, I think I may have gone too far and I really only need ax plus b down there.
Yeah, so that's where I'm confused is that the complementary solution has to be different than the particular solution, or like f of x has to be.
If any yp term contains things that duplicate terms in yc, then we must get more x's multiplied in until it is different than the stuff in yc. So I'm wrong, and we only need x e to the 4x because I'm only trying to make it different than this, not that. Multiplication rule 2, page 148.
So would it be wrong to have added the x squared?
No, it just means I'm going to end up with an extra variable and I have to solve 3 equations in 3 variables rather than 2 equations in 2 variables, and I should end up with a being 0. So the reason I only need an x in the e to the 4x part is because I'm trying to compare it with this thing, not with that.
So technically, you wouldn't need the b.
Yeah, because stuff would get sucked up, right? Whatever I find, I'm going to have, let's say this turned out to be 2x plus 5. But I can say 5 e to the 4x, doesn't that 5 just go into here? Yes. Again, I'm being a little rigid and hidebound here and being a pain in the ass. But if I've got an x to the p, I should have a complete polynomial of degree p, just to cover my butt.
So it would be like if the highest power was duplicated, then you multiply.
By 1 more. Yeah. So in this case, it's x to the 0 that's here, so I multiply by a single x. If it wasn't, let's say we had a repeated root. So I'll change one number. Y double prime plus 2y prime plus 1y equals 16 minus x plus 2 e to the x. I'm going to have to change 2 numbers. So this, when I solve y double prime plus 2y prime plus y equals 0, that's r squared plus 2r plus 1. That's r plus 1 squared. Oh, I missed. that make this e to the minus x. There. Then I get r equals -1 twice, so I get c1 e to the minus x and c2x e to the minus x. But up here I already have, I see the e to the minus x again, right? I should put an x next to it so it doesn't duplicate this. But if I put an x next to it, it duplicates this, so I need to put an x squared next to it. Yp should be number plus something x squared e to the minus x. Because if I just had no x's, it'd be this. If I had one x, it would be this. I need at least two x's to get rid of the duplication.
So we multiply the whole thing by x or just the one term?
Just the one term. Because that's the only piece that's got duplication, right?
I thought they both have duplicated,
This?
but in the,
Oh, you mean both of these terms? I'm multiplying this thing. Right? That's the thing that's duplicated, the e to the minus x. Let me write this up here as 16 minus x e to the minus x minus 2 e to the minus x, right? My particular solution should have an e to the minus x in it. It can't just have number e to the minus x because that's already here. It can't have x e to the minus x because that's already here. So it's got to have an x squared e to the minus x to miss these things.
x squared plus bx plus c.
If I really wanted to be anal retentive, yeah, it should be a plus bx squared plus cx plus d e to the minus x. But now I know that whatever I'm going to get for this number c, I'm just going to add it to this number. And whatever I get for d, I'm just going to add it to this number. So those are already there. But me being the guy that I am, I'm going to write it all the way down. Which I said, oh, I should have an x squared in it. All right, that means I should have a complete quadratic. Yay! It makes sense now. Write down some more stuff so it makes sense later too. Mia, can I make it sound like linear or will you throw something at me?
You can try it.
If we think about the idea of being linearly independent, in functions, we think of the Wronskian. So what I'm trying to say is I need something that's not in the span of the vector space created by e to the minus x and x e to the minus x. Well, I can get any number times e to the x I want. I get any number times x e to the minus x I want. What I can't get, no matter what I do there, is an x squared. And so I want something that's outside of this span, so it points in a different direction. And that's what this does. Now, the cx and the d will get absorbed into the span, but the x squared part won't. And it'll continue to stick out in a new direction for our particular solution. So very much Graham-Schmidt process, where I add in a new vector so I can go in a new direction. Linear and diffie-q go together so much. This is where most of my visual imagery starts to come apart because I keep thinking of vector spaces like arrows, right? In the universe of functions, the set of functions is an infinite dimensional vector space. So the images I have for all the finite dimensional vector spaces start to fall apart. And I have to kind of take it on faith that the same rules apply. They get tweaked a little bit as we go out to more and more dimensions, but it works in the long run. There's a whole discussion in another course that we don't teach here called functional analysis, which talks about something you did in 207 about convergence, right? And I can ask, does the set of functions I'm using as a basis really span everything? Well, then the question is there a sequence within the basis that converges to my function? And that's where things like uniform convergence show up. And I know that's in the 207 course. And this is where we start to reach the limits of what I really did well with in functional analysis and get to the stuff from like, I think I understand what's going on here, but not 100%. More stuff. Yes.
Could you, like, maybe try to find a way to explain 10 or 5.1, 10 for C?
10C. 1, 10C. Use one of the solutions obtained in part A or B to determine the times the mass attains a displacement below the equilibrium position equal to half the amplitude. Okay. So in part A and part B, you rewrote it as one giant trig function, right? So do you want to use the sine version or the cosine version? So I have A sine omega t plus phi, right? And that looks something like that, right? And it's as high as A here and as low as minus A there. Whoop. There we go. But a sine curve would normally go through at 0, but because of that phase shift phi, we're off by that. Yes? When we set this up, we set down as the positive direction, right?
Yeah.
So what I want you to do is find for me the first times, the first t values, because that's what this axis is, that's t, where we hit that line, which is exactly halfway down, isn't it?
Yeah.
Well, all you have to do is set this equal to a over 2.
So as long as I find A,
Which you found in parts A and B, right?
I'm solving for T.
Right. Tell me when we hit this line. Now, it should happen infinitely often, right? Because this is undamped vibration.
Yeah.
So it's going to keep going back and forth forever. So you're going to hit it infinitely many times. But when you go to solve that, you're going to end up with sine of something equals, which is going to give you this multiplication of n pi, right? I can get there from here. So what is this actually physically telling me? If I think about my spring system, I don't know what number you came up with in part A or B, but let's say it was 2. The amplitude is 2. This is telling me, since I'm going to go down to 2 feet and stop and come back up, this is telling me when I cross the 1 foot mark in each direction. Now, I guarantee you that the problem is that some of these are going to suck because phi is an ugly looking decimal, right?
Yeah.
So we'll just deal with it as ugly looking decimals. That's all right. Humble. Ask me more things, people. By the way, you can do this with the cosine as well, if you're well. So Mia, the past several times I've tried, I went back to that math 24 thing. It let me in, but it gave me errors every time. So I'm still trying to figure out what happened. Until then, I took the link down. I did add this video on complex numbers as rotations. Because that's actually the introduction to tomorrow. In a very real sense, figuring out why complex numbers act as rotations is something, as soon as you study the way that RE to the I theta function works, is straightforward. But why do we want to use them? Well, it turns out that tomorrow, when I start to talk about the Laplace transform, it's really based off of this idea. And I'm doing in complex numbers the auxiliary equation. And this particular video happens to launch. Go away. It says right there, Laplace transform prelude. The second video of this went up, and it goes through the definition we're going to go through tomorrow. And I must tell you, they're not terribly long videos, but they are really illustrative in a way that makes me feel inadequate as just saying, hey, let's go through the definition and we'll worry about why it works later. You should watch these videos. If not before tomorrow, then definitely over the weekend. Because they're going to make what we do with the Laplace transform make so much sense in a new way. But that's for tomorrow. What else do you have for me here? Because seriously, he launched the videos and I went, oh, an hour, I don't have to teach. Look, watch the video. It's really cool. Clock on the wall says I got 40 some odd minutes of your time left. Talk to me. Or we just sit here, be bored with each other. Tomorrow, immediately after class. The review sheet key and the homework keys. Well, I mean, you can already tell I would set up those formulas for phi right there, right? So I would definitely write down that trig simplification thing. I'd probably write down the base conclusions we had, right? When you have two reals, one repeated real, one set of complex. When I see these roots, this is what my solution should look like. When I see these, the Cauchy-Euler equations, the one from chapter 4, section 7, they're different. They're not e to the whatever. I'd probably put that down. Mia, you were asking me about writing up the undetermined coefficients things, right? Well, back on page 147, there's this gargantuan list. I might write some general rules here, like polynomials give me polynomials, trig functions give me trig functions. Products give me products, sums give me sums. And then, oh, don't repeat stuff that shows up in YC. I don't think I'd write down this whole table because it's pain in the butt, and it does say no particular examples, and that's exactly what these are. So I wouldn't write that down, but I might try and use this to generalize some stuff. I'd write down whatever integral formulas you think you've forgotten. Integration by parts, trig integrals, things like, we did a bunch of crazy integrals, but I'm trying to avoid as many of the crazy ones as possible. But still, that means, I don't know, I might have to do the integral of x cosine x. Didn't it show up as one of the things that was just in that list? Yes. Do I like it? No. But I need it. And then for the spring setup, I would write down what the numbers are. K and beta and M and period and frequency and things like that that were given to us at the beginning of that section, depending on how much physics you remember versus what's melted out of your head. Because it melts out of mine pretty quickly. The reason we bother doing springs and spring mass systems is because fundamentally they are part of the reasons calculus was invented, to understand all of the physics that's going on in vibrating behavior, from sound, which is vibrating air, to turbulence underwater, vibrating water, to motion through the air of the surface of a plane, the vibrations going along the fuselage tube itself. The goal was to understand how these vibrations happen. And in the case where we've got both a damping coefficient, like the air slowing us down, and a full vibration behavior, the problem is the non-homogeneous part. Reduction of order and variation of parameters suck. They're not fun. Figuring out that right-hand side, what should it look like, and guessing, pain in the neck. But the bigger problem is continuity. The one we did yesterday, what was our forcing function yesterday?
For the driven motion.
Yeah.
next.
But what was the f of t part in the example we did at the end of class? It's a trig function, right? 10 something.
Yeah, 10 cosine 3t.
Okay, so that's what's happening on the outside, right? That's what's being pushed into my system. In the homework, Mia, that you were asking me about at the very beginning, the two graphs, that was set up equal to some trig function, right? Well, a cosine and a sine, yes?
Yeah.
So those are wonderful and great ideas. But most forcing functions aren't continuous. If you want to start something vibrating, how do you do it? But you just do it once, right? Go down to the dining hall, grab a fork, and smack it on the table this way, vertically. Put it to your ear, you'll hear it vibrate, right? But what you did was a single strike. That's not a continuous behavior. You hit it and stopped. That's definitely a discontinuous function. I have an electric circuit. Electric circuits behave just like vibrating springs. I turn it on. It went from 0 to 1. There's no in between. It just click, it's on. I threw the switch, pulled the lever. Same idea, right? Boom, it's on. That's not continuous. Integrals? No. When I start doing not continuous things and I try and integrate, my integrals tell me to go F myself. So just like we said, it's easier to work in the auxiliary equation. It's easier, instead of working with derivatives, to work in algebra. I want to find a way to convert functions that are ugly and hard to integrate and nasty to deal with into algebra problems. Even if those algebra problems are nasty and hard to deal with, they're just freaking algebra. And that's going to be my overarching goal with the Laplace transform. But rather than me ramble about it for another half an hour, if you don't have any more questions, I'm going to tell you to get out of here. If you've got questions, start asking them. Jack?
In like sorry, the Cauchy stuff.
Oh, with the Cauchy setup, yes.
Yeah. Like a repeated always use that same like you have to show everything.
No, we can use the same thing at the same time. And it's always going to be an ln.
Yeah, okay.
Right, just like in that one, it's always going to be an x.
Yeah,
I don't have to go through the reduction of order to show it.
okay.
No, you don't have to do that from scratch. That would be something that goes on my sheet. Right, Hayden? Yes, let's force ourselves to do the giant integral trick that always results in the same answer. No. I'm not leaving, but if you are, I'll see you tomorrow. I got no place else to be till 2 o'clock when I have a meeting with Burns.
Well,
You too, Hayden.
we did it.
See you, Cody.